During the next few weeks, we're going to be covering Chapter 7. The goal of the first few sections is to learn various other tools for computing definite and indefinite integrals. One of the things you always want to try to look for is a simple way first. For example, here are two indefinite integrals. So for each of these, the results should be a family of functions. Always, always, always look to see if the functions inside that you're trying to anti-differentiate are on the list, and then use properties of linearity. So for example, 3 is just a constant, and we know that the antiderivative of 2 to the x should appear on the list, and in fact it does. So this will be 3 times 1 over the natural log of 2 times 2 to the x. And the only way I know that is because I remember the antiderivative of 2 to the x from the list. The antiderivative of sine of x is minus cosine of x, not just cosine of x, because that would be the derivative. We want to make sure we compute the antiderivative. And then x to the square root of x can be converted to a power, x to the 1/2. So using the power rule with n equals 1/2, or n plus 1 equals 3/2, the antiderivative would be 1 over n plus 1, which is the reciprocal of 3/2. That gives me 2/3, x to the 3/2 plus our arbitrary constant. Now we could, of course, check the answer by computing the derivative. Now, if we don't see the functions on the list, the next thing we need to do is we need to think about algebraic simplification. In this example, we can break the fraction up into 2, use properties of exponents. So this will be the indefinite integral of, let's write this as x to the 1/3 over x squared plus x over x squared. Now simplify our exponents. We subtract exponents, so 1/3 minus 2 is the same as 1/3 minus 6/3, or x to the minus 5/3, plus 1 over x. Now, for this first example, we use the power rule. N is minus 5/3. N plus 1 would be minus 5/3 plus 3/3, which is minus 2/3. So we would take 1 over n plus 1, which is minus 3/2, x to the minus 2/3. And of course, we could compute the derivative of this, and we should get x to the minus 5/3. And then we add to that the antiderivative of 1 over x, which is, we need to be careful here, it's the natural log of the absolute value of x. Okay, now if algebra doesn't work, we need to use a different technique, and that's the goal of section 7.1. So to use this technique, we need to be able to use the chain rule proficiently. So I'm going to start with the function, a simple function, the derivative with respect to x. Let me focus this again. Okay, derivative with respect to x of sine of x to the 3rd plus 1. Now, I'm going to go through the chain rule fairly quickly, and you may have learned different ways of using the chain rule, and use whatever way works best for you. But I like to think of an inside and outside function. We take the derivative of the outside function, which is the cosine, evaluate it at the inside function, multiply the result by the derivative of the inside. So we take the derivative of the outside, which is cosine, plug the inside function is there, and then we take the derivative of the inside function, which is 3x squared. Now we could write this derivative statement as an anti-differentiation statement as well. So in other words, the antiderivative of cosine of x to the 3rd plus 1 times 3x squared dx is equal to the sine of x to the third plus 1 plus an arbitrary constant. Here's another example. Let's compute the derivative of the square root of x squared plus 3. Now this is a fractional exponent, so I could write this as the derivative with respect to x of x squared plus 3 to the 1/2, and using the power rule for derivatives, this would be the derivative of the square root function, evaluate at the inside function, subtract 1 from our power, and then multiply by the derivative of the inside function, which is 2x. Now we could write this as an indefinite integral statement. The indefinite integral of the 2's would cancel, of x squared plus 3 to the minus 1/2 times this x dx is equal to the square root of x squared plus 3 plus our arbitrary constant. Okay, now here's what I want you to recognize about each of these two examples. Each of these two examples, we were taking the derivative of the chain rule. So if we think about the chain rule in reverse, the antiderivative of that, the antiderivative is this, the antiderivative is this. Take a look at what's common with both of these integrals. In each of these two, we have the product of two expressions. The product of two expressions. Now, one of these expressions, if we compute the derivative of something appearing in the expression, we get the other expression, but perhaps missing a constant. So for example, if we look at x squared plus 3 and we take its derivative, we get 2x, which is close to this, except it's missing a constant. If we take the derivative up here of x to the third plus 1, we get 3x squared. So in each of these examples, we have the product of two functions, and somewhere the derivative of one expression is appearing. So this is the idea of integration by parts, is to capitalize upon this fact. Let's take a look at an example. The indefinite integral of e to the x to the third, whoopsie, I want to change this. The indefinite integral of e to the x to the third times x squared dx. Now this is a product of two functions, and we see that the derivative of x to the third is 3x squared, which except for a missing 3 appears right here. Let me say that again. We have the product of two expressions, and inside one of the expressions we have an x to the third whose derivative is 3x squared, and that 3x squared appears here, except the 3 is missing. So the idea of integration by substitution is that we do a temporarily relabeling. We saw the x to the third appearing here, so we let u be x to the third. Its derivative is 3x squared. Now we take this integral, which is in terms of x, and we rewrite it completely in terms of the new variable u. So for example, e to the x to the third becomes e to the u, and now x squared dx, we can calculate what this quantity is by manipulating the derivative. If we cross multiply and divide by 3, du divided by 3 is equal to x squared dx. And that means that we can replace this expression with du over 3, or 1/3 du. And if we antidifferentiate this, we get 1/3 e to the u plus a constant. Now, we were computing the antiderivative of e to the x to the third times x squared, which is in terms of x. So we want an antiderivative in terms of x, and what we do at the very end to get that is we back substitute. We go back and look at what u was, and we replace it in this formula. So we get 1/3 e to the x to the third plus c. So that's our indefinite integral. And how would we check this? We would compute the derivative of this expression, and we would use the chain rule, and we would get exactly what we have right here. So you can always check by using the chain rule. Now this method is sometimes known as the substitution method or the u substitution method, because typically we use u as the new variable. Let's take a look at another example. The indefinite integral of 2 to the sine of x cosine of x dx. And I should put this on autofocus lock. Okay, that's pretty close. Now, the first thing we always want to do is we always want to look and see if the function we are trying to anti-differentiate appears on the list. And in this case, it does not. The next thing we do is we always look for algebraic simplification. And you need to take a look at this and verify that there is no algebraic simplification. Okay, then we start to think about this method of substitution. Don't think about substitution until you've thought about looking at the list and algebra simplification first. Now again, we have the product of two functions, and we see in one of the functions, we see an expression whose derivative appears in the second expression. So if we look at this first expression, we see appearing in it the sine of x, and its derivative is the cosine of x, which is appearing right here. So in this case, we let u be the sine of x. So let me say that again. We see an expression appearing in the first product term. We see an expression, that's what u is. Its derivative appears elsewhere. So the derivative of u is the cosine of x. Or, in other words, cross-multiplying, du is cosine of x dx. Now let's rewrite the original integral in terms of u. 2 to the sine x would become 2 to the u, and the cosine of x dx is simply our du right here. Now we can anti-differentiate this because it's on the list. The antiderivative would be 1 over the natural log of 2 times 2 to the u plus a constant. And again, we have to back substitute. So this becomes 1 over the natural log of 2 times 2. U was sine of x, and then we add our constant. And again, we could check, and we would check by computing the derivative of this. We'd be required to use the chain rule. The method of u substitution is really just the chain rule in reverse. Let's take a look at a third example. And let's make it a definite integral. The integral from x equals 0 to x equals 1, 3x squared plus 1 to the third times x dx. Now, what's different about this is it's a definite integral. Okay, there are a couple ways to handle this, but we know the result should be a number. Okay, we don't see this function on the list. We could algebraically simplify this by expanding this cube, but that would be a real pain. So let's look for a simpler way. We see that we have a product of two expressions. And inside one of the expressions, we see something whose derivative appears in the second expression. In other words, if we take the derivative of this, we get 6x, which is very close to x, except we're missing the 6. That's not a problem. That's not a problem at all. So we let u be 3x squared plus 1. Its derivative is 6x. And if we cross multiply and divide by 6, this tells us that du over 6 is equal to x dx. Now we're going to rewrite the original integral in terms of u. The inside becomes u to the third, which is just this. X dx is 1/6 of du, but we could pull that 1/6 out. Now, the endpoints. There are a couple options. Remember, this is a definite integral. There are a couple options. One option is to anti-differentiate this, back substitute, and plug in the endpoints. In other words, anti-differentiate u to the third, replace u with 3x squared plus 1, and then evaluate at our two endpoints. That's one way to do it. But I prefer to do it a different way that sort of streamlines the process. Let's take a look at our endpoints. Our original endpoints were x equals 0 and x equals 1. Now, our substitution says that u is equal to 3x squared plus 1. So if we plug 0 into that, we get 3 times 0 squared plus 1. So that means I'm going to replace the endpoint of 0 with 1 for the lower endpoint. U equals 1. The original upper endpoint was x equals 1. If I substitute that in here, I get u equals 4. So that becomes the new upper endpoint. The difference between this approach and back substituting after anti-differentiation is that I won't have to back substitute here. Let's simply compute the antiderivative. 1/6. Using the power rule, we'd have u to the fourth over 4. And we would evaluate that at u equals 1 and u equals 4. We don't need to replace u with x now. We're basically done. This would be 1/24 of u to the fourth. I'm sorry, of 4 to the fourth if we plug in our upper endpoint, and we would subtract what we get when we plug in 1. 1 to the fourth. And we can simplify this using a calculator or just basic arithmetic. Now, the hard part about this technique of substitution is choosing u and then going through this algebra of computing the derivative and then rewriting the new integral in terms of u. That's hard, and only through lots of practice will you actually discover how to do it fairly quickly. So here are a couple of problems I want you to work on for class. One of these will be an indefinite integral, the integral of e to the tangent of x times secant squared of x dx. And the other one is going to be a definite integral, the integral from x equals 0 to x equals 2 of x over 1 plus x squared dx. Now, this will be a family of functions. This will be a number. Now, recall that for this method, we are always looking for a product of two functions. Division is the same as multiplication. We can write this as x times 1 over 1 plus x squared. In this example, it's not clear what the substitution variable u should be, but try letting it be 1 plus x squared. I'll give you that hint. And compute this quantity. Your answer should be an exact value. Okay? We'll be practicing this a lot more in class the next few days.